Artificial eyes have played a vital role in restoring confidence and appearance for individuals who have lost an eye due to various reasons, dating back to ancient civilizations. Over time, the methods of crafting artificial eyes have evolved significantly, combining ancient techniques with modern technology to create lifelike prostheses. In ancient Rome and Egypt, artificial eyes were crafted from painted clay, showcasing early attempts to restore visual appearance. By the 1500s, Europeans advanced the art by fashioning artificial eyes from enameled gold and later glass, which remained the norm for centuries. Today, most artificial eyes are made of acrylic, marking a shift from traditional materials. The process begins with an initial consultation with an ocularist, who specializes in fabricating ocular prostheses. During this consultation, the patient's needs and preferences are discussed. Once the patient is ready to proceed, the ocularist takes an impression of the eye socket using a specialized material known as alginate, a white powder made from seaweed that is mixed with water to form a cream, which is also used by dentists to make impressions of gums. This impression captures the exact size, shape, and contours of the eye socket, providing a blueprint for creating the artificial eye. After the impression is taken, it's time to make a mold. They place the impression in a mold and pour in a type of plaster. After the plaster has hardened, they remove the impression and what's left is a plaster mold of the socket. Now they pour a wad of acrylic plastic dough into the mold, lock the mold in a press, and place it in an oven to cure. The acrylic model that emerges from this process is known as the fitting shape because they use it to fit and mark the position of the fake iris. They accentuate the markings and then attach a peg with a drop of wax. The peg indicates the natural angle of the iris when the patient is looking forward. More wax is added around the perimeter to enlarge the fitting shape. This excess will give the ocularist some room to work with for the final sizing. This enlarged fitting shape is placed into a plaster mold once again. This mold will be used to cast the actual artificial eye once the iris is prepared. The iris, or colored part of the eye, is painted onto a flat plastic disc, which is measured to the size of the patient's remaining iris. Each iris is hand-painted using oil-based paints, and the technicians work from either a digital photo or a previously painted eye to make sure that it will match the other eye. After 18 hours, the iris paint is finally dry and it gets pressed into a button-shaped disc. This puts a curve on top of the iris so it'll be flush on top of the round eye. The iris is placed upside down into the mold that was prepared beforehand and the white of the eye is made. It's made out of ploy methacrylate, a medical-grade acrylic plastic similar to the material that's used to make false teeth. Once prepared, it is squashed down into the cast on top of the iris, and the whole mold goes into an oven for 2.5 hours. The eye is now starting to take shape. The excess material is trimmed away on a grinding wheel, and the eye gets stained and veined. The average human eye isn't snow white, so a bit of watercolor paint is dabbed around the edges depending on the patient's natural color. This embroidered silk is used to replicate the veins of the eye. The thread is separated into individual fibers and applied with an acrylic varnish. Just 1 centimeter of this thread will provide enough fiber to make over 100 eyes. A coat of clear acrylic varnish is applied over the top of the eye and it gets oven cured to seal it. Finally, a buff and a polish give it a nice, glossy finish and the appearance of a living eye. The expected lifespan of an artificial eye is around 6 years as long as it gets looked after properly. Once the artificial eye is polished and finished, it is ready to be fitted into the patient's eye socket. The ocularist carefully inserts the prosthetic eye and makes any necessary adjustments to ensure a comfortable and secure fit. This may involve trimming the edges of the prosthesis or making minor modifications to improve alignment. Before the patient leaves the ocularist's office, they receive comprehensive education on how to care for and maintain their artificial eye. This includes proper cleaning techniques, hygiene practices, and instructions for handling the prosthesis. The patient is also advised to schedule regular follow-up appointments with the ocularist to monitor the fit and condition of the artificial eye. In 1957, the American Society of Ocularists, or ASO, was established to raise standards and provide education for the ocularist. In 1971, the ASO began to certify ocularists. Those who already had well-established practices were automatically certified. Others had to complete a 5-year apprenticeship under the direct supervision of a previously certified ocularist and complete 750 credit hours of related instruction approved by ASO. In 1980, the National Commission of Health Certifying Agencies, or NCHCA, created an independent testing organization for ocularists called the National Examining Board for Ocularists, or NEBO. In November of 1981, NEBO administered the first national board certifying exam. Board-certified ocularists must be recertified every 3 years. To achieve a fellowship in ASO, a board-certified ocularist must accumulate 375 additional credit hours of related instruction and have demonstrated outstanding ability in their practice. Advancements in computer, electronics, and biomedical engineering technology have resulted in the invention of bionic eyes. Bionic eyes, also known as retinal prostheses or artificial retinas, are advanced medical devices designed to restore vision in individuals with severe visual impairments, such as retinitis pigmentosa and age-related macular degeneration. These devices work by bypassing damaged or non-functioning retinal cells and directly stimulating the remaining healthy cells to transmit visual information to the brain. These kind of eyes, while representing a significant advancement in vision restoration, have several limitations. These include a lower resolution compared to natural vision due to the limited number of electrodes in the retinal implant, resulting in a restricted visual field and potential tunnel vision. Implantation requires invasive surgery, posing risks such as infection and tissue damage. Additionally, bionic eyes may not offer the same level of visual acuity or depth perception as natural vision, impacting tasks requiring precise depth perception. Adjusting to the visual input from a bionic eye can also be challenging, requiring an adaptation period for the brain to interpret artificial signals. Furthermore, the high cost of bionic eyes makes them inaccessible to many individuals with visual impairments, particularly those from disadvantaged backgrounds. However, research is being done to create new devices as well as improving outcomes with existing devices. Prostheses are being refined to make the lifespan of devices longer, improve quality of life with more powerful and smaller devices, expand the field of vision, increase the number of electrodes, and improve clarity and sharpness of vision. Although they sound like a recent invention, hearing aids have been around as early as the 17th century, although at that time they weren't as small and nifty as they are today. They were in the form of large trumpets that increased the audible sound pressure to augment hearing difficulties. Today, tiny aids placed in the ear canal are barely visible to others. But how are they made? Before production of the hearing aid can begin, the degree of hearing loss is processed by an apparatus known as the audiometer. Much like a test for weak eyesight, the audiometer test is designed to measure the extent of hearing loss for a person. The result of the test is in the form of an audiogram, a chart that shows how well a person hears in terms of frequency and loudness. The next step is to make a mold for the ear canal. This is done so the hearing aid can be designed to very precise measurements. An auto block is inserted in the ear canal to protect the eardrum from damage while making the mold. Once done, a silicone impression making material is inserted into the ear. Once it solidifies, it is removed from the ear. Now that the audiometer test is done and the ear impression is taken, all order data, desired product features, and the results of the test are entered into a computer to determine the operating range for the hearing aid, specifically which levels of amplification are required for the user. For some manufacturers, the computer also selects the electronic circuitry to be used. Typically, an order card will be prepared and sent to the production line along with the ear impression. The jelly-like mass of silicone that was removed from the ear will be used to make a positive imprint. It is soaked in warm wax, forming a solid film over the impression. It is then placed in a silicone cup. The cup is then filled with silicone, which solidifies in only 10 minutes. The hardened silicone block is removed from the container. Then the silicone impression is removed from the block, leaving a positive imprint. The case of the hearing aid can be made from this mold. The mold is first heated in 110 degrees Fahrenheit or 43 degrees Celsius water, and air is blown through it to clear away any impurities. At this point, a technician will mix liquid acrylic of equal parts monomer and polymer for a structurally sound shell and add the desired pigment to give the shell a pink, tan, or brown color. The technician pours the liquid into the heated silicone mold and after 10 seconds pours off any excess, leaving a thin acrylic shell inside the mold. After 10 minutes of cooling, the technician pulls from the mold a shell that is a perfect replica of the raw impression of the ear canal. Today, the entire process of making an acrylic shell from the silicone impression can be done within minutes via a 3D printing machine. Whether produced via 3D printing or manually, the shell still has to undergo finishing touches before it can house all the hearing aid components. After the acrylic shell is prepared, a technician grinds off the excess flanges from the shell. He will then add a vent or opening. A small piece of silicone wire shaped to the vent size is run through the inside of the shell and pulled out. The technician drills holes into the canal end of the shell for the receiver tube. After that, the outside of the shell will be buffed to a smooth, shiny finish. A technician will size the shell for a faceplate or flange, the area that will be exposed outside the ear canal, using the vacuum form from the original impression. The plate will be carefully set at the correct angle for the user's ear. Now, on to the various components that make the hearing aid. Working off of the results of the audiogram, audiologists and engineers work together with advanced computer-aided design, CAD software, to create the components that meet the specific needs of individuals with hearing loss. Once the design is finalized, manufacturing can begin. Hearing aids consist of various components like the microphone, amplifier, receiver, and battery. The microphone is the first component that captures the surrounding sounds. It converts acoustic signals, sound waves, into electrical signals. The electrical signals from the microphone are then sent to an amplifier. The amplifier increases the intensity or amplitude of the electrical signals, effectively making the sounds louder. After signal processing, the amplified and tailored electrical signals are sent to the receiver or speaker. The receiver converts these electrical signals back into acoustic signals, essentially reproducing an enhanced version of the original sounds. All of these are powered by batteries, which provide the necessary energy to run the electronic components. Depending on the type of hearing aid, batteries can be disposable or rechargeable. The components and circuits are run on a ceramic substrate base of various designs. The substrate is made of a screen printing technique that alternates layers of conductive and insulating materials depending on the engineered design. The conducting layer contains gold, silver, and the insulating layers contain silicone compounds. Between the printing of each layer, the substrate is passed by a conveyor through a furnace where it bakes for 2 hours at 850 degrees Fahrenheit or 454 degrees Celsius. This seals the layers and creates the color patterns characteristic of printed circuit boards, only on a smaller scale. The various electronic components are bonded by hand to the gold and silver parts on both sides of the substrate. A technician will interconnect the devices using gold wire of 0.001 inch or 0.025 millimeter thickness. Lastly, the components are sealed in an epoxy paste and heat hardened. Working from the parts card or bill of materials determined at the outset of production, a technician assembles the electronic hardware on the faceplate where holes have been drilled for mounting the microphone, amplifier, battery compartment, and volume control, all hand-wired with colors for traceability. The wires are soldered into place. After this, the receiver is mounted into the shell and a preliminary hearing check is made on the instrument. Rigorous quality control measures are implemented throughout the manufacturing process. Various tests are conducted to ensure that each hearing aid meets the specified standards and performs as intended. This includes functional tests, acoustic measurements, and inspections for any defects in the casing or components. Hearing aids are also tested using a computerized ANSI, American National Standards Institute, program that analyzes the production parameters and produces a performance chart. A technician reviews the chart on screen, checking tolerance levels and other specifications. He or she will print a copy of the results and include it with the finished hearing aid. Hearing aids have come a long way in today's time and age. Customized aids can be programmed to be linked to an app or on your phone, allowing you to adjust the settings at the touch of a finger. In fact, hearing aids aren't just used for hearing anymore and can also be used to translate languages in real time, like something out of a sci-fi film. Before the hearing aid is packaged and sent to the end user, a final round of testing and calibration is conducted. This ensures that the device functions accurately and consistently. Once the hearing aids pass all quality control checks, they are packaged for distribution. The packaging is designed to be user-friendly, providing clear instructions on usage, maintenance, and any additional accessories. Hearing aid manufacturers are continually investing in research and development to improve technology, enhance performance, and address the evolving needs of individuals with hearing loss. If you like this video, there are plenty more on our channel, so be sure to check them out.